Are you tired of lugging around kilograms of equipment or worrying that a student may break something? If so, this presentation may be relevant to your interests. Hi, I am Daniel Friesel, a PhD student at Osnabrück University, and I'd like to show you how to use the EnergyTrace technology embedded in TI MSP430 Launchpads, such as this one, for automated energy benchmarks and energy model generation. So basically, this is a talk about yet another measurement device, though a device with two interesting attributes. First, at less than $20, it's very cheap. And second, it's portable and works right out of the box. There is no need for firmware hacks or soldering. Of course, there's also some downsides. There are no publicly documented accuracy figures for EnergyTrace, and it lacks synchronization support, so it cannot be used with conventional automated measurement methods. Nevertheless, we set out to determine how accurate it actually is and whether it can be used for automation, and as it turns out, yes it can, and it's sufficiently accurate for most use cases. First, some key findings. EnergyTrace measures energy at a 3.7 kHz sample rate, constant voltage of 3.3 volts, and with a maximum measurement range of 20 milliamps, so not that much. With calibration and our synchronization method, current measurements exhibit a maximum error of 5.2% in the microamp range and 1.2% in the milliamp range, and synchronization signals generated by our synchronization method exhibit a maximum error of 1 millisecond. Next, I'll give a quick overview about the MSP430 Launchpad and our automatic model generation framework, and then present our key contributions, a synchronization and drift compensation approach for devices which lack conventional synchronization mechanisms. For details about our benchmarks and evaluation, please refer to the paper. The MSP430 Launchpad is an evaluation board for MSP430 microcontrollers that's been around for a few years already. It consists of a target microcontroller with GPIOs and LEDs, a debug interface for programming, debugging, and USB to UART conversion, and an EnergyTrace circuit which measures the energy consumption of both target microcontroller and all connected peripherals. There's also a set of jumpers, so it's possible to measure the energy consumption of external devices as well. Our model generation framework is based on prior research. The basic idea is, given a microcontroller and a peripheral device, all a user needs to do is provide a device driver and hardware model, connect the device to the microcontroller, and tell the framework to get going. The framework then automatically generates a benchmark, executes it, and analyzes results, and the user is provided an energy model. For instance, given a TI CC1101 radio module, the device model indicates how the different driver functions interact with different hardware states, and the energy model is basically the device model augmented with duration and energy data, though most models are more complex than this example. A key component of the automation aspect is synchronization of measurements. During analysis, the algorithm needs to know which measurement corresponds to which hardware state or driver function. To achieve this, we use an I/O pin which is toggled whenever a benchmark event occurs, and in this case benchmark events are the start and end of driver function calls. The I/O pin must be connected to the synchronization pin of a compatible measurement device, which logs not just energy data but also the state of the I/O pin. And this is precisely what EnergyTrace lacks. EnergyTrace measures energy only, it's entirely independent of I/O, UART, or similar events. So we need to come up with a synchronization method. This consists of two parts. First, we use the Launchpad's onboard LEDs for in-band signals, indicating the start and end of the benchmark. And then we use one of the MSP430's onboard counters to count the CPU cycles between benchmark events, starting at the first synchronization pulse and ending at the last. This allows us to calculate the EnergyTrace timestamp of each individual benchmark events. To a certain extent, as EnergyTrace and CPU timer are fed from different clocks, they react differently to random temperature fluctuations and drift apart over time. In our measurements, the worst drift we observed was 1.5 milliseconds per minute. So for a 10-minute measurement, a synchronization timestamp may be off by up to 15 milliseconds, which is definitely too much for most use cases. To overcome this, we also developed a simple drift compensation algorithm. The basic idea here is that, given our uncompensated timestamps calculated from the CPU timer, we assume that most benchmark events correspond to observable changes in the device's energy consumption. So we use a change point detection algorithm to detect these change points in the observed energy consumption, and now only need to determine the correct change point which corresponds to the actual or compensated event timestamp. Except we don't know which one it is, at least not in general. But there is one thing we do know, and that is the effects of drift accumulate over time. So if two benchmark events are close together, they will have nearly the same drift. And this drift or synchronization error is identical to the difference between compensated and uncompensated timestamp if the compensated timestamp has been selected properly. So if we know the compensated event timestamp or change point candidate for one benchmark event, then we should select the candidate for the next benchmark event that leads to nearly the same drift. Or phrased another way, the difference or the evolution of the effect of drift should be minimal. Not just for each pair, not just for one pair, but for all pairs. So in the end, we have a pretty simple optimization problem. And in fact, this already is the key component of our drift compensation approach. So given a series of timestamps t corresponding to benchmark event and candidates for each individual timestamp, which are shown here on the y-axis with the corresponding drift, we first initialize our algorithm with candidate sets for the first and last timestamp. These coincide with the in-band signaling synchronization signals. So by definition, the error is 0. Next, we perform change point detection to calculate the candidates for the remaining timestamps, and then select compensated timestamps from these change points so that the evolution of drift over time is minimal. With proper modeling, this is as simple as a shortest path search in an undirected weighted graph. And here is the shortest path for this example. Going back to the drift plot, this is the synchronization error without drift compensation, just synchronization. And here we see the synchronization error with drift compensation, which is much lower and constant. In fact, this algorithm works for any device which is capable of generating in-band synchronization signals and has a timer and UART or similar communication channel to communicate the calculated benchmark event timestamps. Of course, there's also some limitations. First, the benchmark must be the only running application, otherwise we cannot assume that change points are caused by benchmark events. And second, at least every third benchmark event must have immediate observable effects. If a benchmark event does not have observable effects, the set of change points and therefore candidates for event timestamps is either empty or contains bogus data. If this doesn't happen too frequently, our algorithm can handle that, but at the moment there are some limitations and presumably these will remain. In conclusion, I have shown how to use the EnergyTrace technology embedded in TI MSP430 Launchpads for automated measurements with acceptable accuracy figures and a cost of less than $20. I've also presented a synchronization and drift compensation algorithm which are not specific to EnergyTrace but applicable to a wide range of devices which lack conventional synchronization mechanisms. Personally, I think this makes EnergyTrace a good choice for quick qualitative measurements, such as determining whether a change in a radio driver has adverse effects on its energy consumption, and settings such as student labs, where you can just buy a box of Launchpads, hand them out to students. If they like, they can even take them home, and if one of them breaks, well, it's just $20.